a certain type of trig identity, a trig identity for sine n theta or cos n theta or tan n theta. Today's lesson, we're going to see how we can use de Moivre's theorem to prove a different kind of trig identity, a trig identity for cos to the power of n theta, or sine to the power of n theta, or even some function which is a product of cos to the m times sine to the n. Now, in order to do this, we're going to use a certain bit of background knowledge, which I'm going to highlight here. It's a method for writing cos theta or cos n theta or sine theta or sine n theta in terms of z, where z is e to the I theta. Now, this is going to be what we're going to need for today's lesson. It would be highly that you may be required to prove some of these results. So I'm going to do that first of all. I highly recommend you find some space in your pack. I hope there's space on the back cover, or if not, you get a spare bit of paper and you make a note of these. I'm going to go through this and then we'll come back to how we can prove these trig identities. So this is basically taken from Active Learn. So it says if z is e to the I theta, I'm going to prove these two statements in boxes. I'm going to prove that if z is e to the I theta, 2 cos n theta is the same as z to the n plus 1 over z to the n, where z is e to the I theta. And 2I sine n theta is z to the n, take away 1 over z to the n. The other two statements are here are basically got by taking the two rules we have and substituting in n is 1. So I'm going to prove to you these two statements. I'll start with I'm going to do them both at once, basically. So basically, here's they come about. So I know that z is e to the I theta, and I know that e to the I theta is cos theta plus I sine theta from what we've done previously. So consequently, z to the n is cos theta plus I sine theta in brackets to the power n, which is equal to cos n theta plus I sin n theta. That is by de Moivre's theorem. That's what z to the n is. I'm now going to write down a similar expression for 1 over z to the n, because both of these expressions involve 1 over z to the n. So 1 over z to the n is the same as z to the minus n, which is therefore the same as cos theta plus I sine theta in brackets to the power of minus n. But de Moivre's theorem works for negative numbers. So that's de Moivre's again with a power minus n. That's cos of minus n theta plus I sine of minus n theta. That's using de Moivre's theorem with a power of minus n. And then I can simplify slightly using the fact that the cos of a negative is equal to the cos of a positive. So cos of minus n theta is the same as cos n theta. The sine of a negative is the same as the negative of the sine. So sine of minus n theta is minus I sine n theta. So what I've got is that z to the n is equal to that, and 1 over z to the n is equal to that. Now, if you add or subtract these two lines, you'll get z to the n plus 1 over z to the n, or z to the n minus 1 over z to the n. So adding those two lines, I get z to the n plus 1 over z to the n is cos n theta plus I sine n theta, add cos n theta minus I sine n theta. That's adding the two lines previously, that plus that. The I sine n theta terms cancel out, and that gives you 2 cos n theta. So that's the first thing that I wanted to prove. If instead of adding you subtract them, you get z to the n minus z to the n is cos n theta plus I sine n theta minus cos n theta minus I sine n theta, those second two terms being in a bracket. This time the cos n theta terms cancel out. I sine n theta, take away a negative means add on I sine n theta. That gives me 2 sine I n theta. Okay, so I've just proved these two statements here in boxes. As I said, if you take this one and replace n with 1, you get that 2 cos theta is z plus 1 over z. If you take this one and replace n with 1, you get 2I sine theta plus z minus 1 over z. Okay, so the stuff here which I've put a circle around in the background theory, is going to be the background for how I can derive identities for cos n theta, sine n theta, or some product of the two of them. It feels a little bit like how we prove the identities for cos of n theta, sine of n theta, but we do it in a different way, ladies and gentlemen, boys and girls. And recently in an exam, when questions of this type have come up, they have told you to let z be sine n theta and either prove or even given you one of these statements. So here is what I'm going to do. So I'm going to use De Moivre's theorem to find a formula for cos to the 4 theta. In a minute, we will show how I can use that to integrate cos to the 4 theta. In an exam, they are likely to tell you you must use De Moivre's theorem, and we use De Moivre's theorem to generate these identities, and it's likely to be a show that question. So this is what I'm going to do. If I want to show a formula for cos to the 4 theta, I'm going to start off with an identity which has got cos to the 4 theta in it. So from what I've done earlier, if z is e to the I theta, I know that 2 cos theta is equal to z plus 1 over z. That's from what we've done earlier. And now I'm going to raise both sides of that to the power of 4. So 2 cos theta in brackets to the 4 is z plus 1 over z to the power of 4. So if you expand the left-hand side, you get 2 to the 4, which is 16 times cos to the power of 4 theta. If you expand the right-hand side, you can do a binomial expansion. A plus b to the n. First term is a to the n, which is z to the 4. Plus 4 choose 1, which you can do on your calculator, which is 4 times z cubed times by 1 over z. Plus the next term, which is 4 choose 2, which is 6 times by z squared times by 1 over z in brackets squared. 1 over z in brackets squared is just 1 over z squared. Plus 4 choose 3, which is 4 times by z times by 1 over z in brackets cubed, which is 1 over z cubed. And the final term is just 1 over z to the 4. I am now going to simplify that. So that is the same as z to the 4 plus 4z cubed times 1 over z is 4z squared, plus 6z squared times 1 over z squared is just 6. Plus 4z times 1 over z to the 4 is 4 over z squared, and the last term is 1 over z to the 4. Now, you will always get a kind of symmetrical expansion in this kind of question. What I'm going to do now is I'm going to pair up the terms involving z to the n and 1 over z to the n. So first of all, I'm going to pair up z to the 4 plus 1 over z to the 4. Next, I'm going to pair up the terms involving z squared and 1 over z squared. I'm going to take out 4 as a factor. So those two terms pair to give me 4 into z squared plus 1 over z squared. And then finally, we have this extra term in this case, which is 6. Now, what I know from what we've done previously, and in fact proved, is that z to the n plus 1 over z to the n is always 2 cos n theta. So consequently, z to the 4 plus 1 over z to the 4 is 2 cos 4 theta. And then z squared plus 1 over z squared is 2 cos 2 theta, but I'm timesing that by 4, and that will give me 8 cos 2 theta plus 6. And remember, this is an identity for 16 cos to the 4 theta. So consequently, to get my identity for cos to the 4 theta, which in an exam is likely to be a show that, you just divide by 16 and you get cos to the 4 theta is 2 over 16, which is 1/8 of cos 4 theta, plus 8 over 16, which is 1/2 cos 2 theta, plus 6 over 16, which is 3/8. That's the identity that we are looking for. Okay, so that's the new bit for today. So can I just go forward it again then, folks? In order to get an identity for cos to the 4 theta, I let z be e to the I theta, so 2 cos theta is z plus 1 over z. Raised both sides to the power 4 and did a binomial expansion on the right. I then paired up the z to the n and the 1 over z to the n terms to rewrite them in terms of cos n theta and divided through by 16. Now, one of the applications of this is they make integration of expressions like cos to the 4 theta, which is difficult. It's a non-linear function to the power of something. The thing on the right-hand side is much easier to integrate than the thing on the left-hand side, because cos to the n theta is hard to integrate, but cos of n theta is easy. So the integral of cos to the 4 theta d theta is the same as the integral of 1/8 of cos of 4 theta plus 1/2 cos 2 theta plus 3 theta theta. Cos integrates to give sine, cos kx integrates to give 1 over kx. So cos 4 theta becomes a quarter sine 4 theta, times it by 1/8 to get 1 over 32 sine theta. Cos 2 theta becomes a half sine 2 theta, times it by 1/2 to get a quarter sine 2 theta. And 3/8 is just a constant which will integrate to give 3/8 theta plus c. That's the integral. That's quite often in questions involving this. In part A, you will be asked to prove an identity, and then in part B, you will be required to integrate the corresponding function. Simple. Okay, folks. So correct one on the next page says, and it's very vague, as I said, with an exam, it's like to say using De Moivre's theorem, and it's likely to be a show that, find an identity for sine up to the power of 5 theta. So from what we've done earlier, if z is e to the I theta, then I know that 2I sine theta is equal to z minus 1 over z. That's from the identity linking sine n theta with z, replacing n with 1. And because I want to raise that to the power 5, I put both sides in brackets and do them to the power 5. So what's that going to give me? Left is just a product. 2 to the 5 is 32. I to the 5, well, I to the 4 is 1 because it's I squared squared, which is minus 1 squared, which is 1. So I to the 5 is just I, and then sine to the 5 theta occurs on the left-hand side, which is good because I want to decide 5 theta. I'm going to have to do a binomial expansion on the right-hand side. So the first term is z to the 5 plus 5 choose 1, which is 5 times z to the 4 times minus 1 over z, plus 5 choose 2, which is 10 times z cubed, times minus 1 over z squared. And if you square a negative, it goes positive. So that's just 1 over z squared. Plus 5 choose 3, which is 10 times z squared times minus 1 over z cubed. But if you cube a negative, you get a negative. So it's minus 1 over z cubed. Plus 5 choose 4, which is 5 times z times minus 1 over z to the 4, which is just 1 over z to the 4. And the last term is just minus 1 over z to the 5. If you do a negative to the power of 5, you get a negative answer. So that leaves me minus 1 over z to the 5. Let's tidy that up a little bit. So that's z to the 5. The next term is minus 5z cubed. Whoops, let me just work that out. Minus 5z cubed plus 10z. And the next one will be minus 10 over z. The next one will be plus 5 over z cubed. And the last one is minus 1 over z to the 5. And then again, I'm going to pair up the terms involving z to the n and 1 over z to the n. This time you'll get minuses, and I'm going to factor out any number in front of the z to the n. So z to the 5 minus 1 over z to the 5, put them together first of all. And then the next two terms are the minus 5z cubed plus 5 over z cubed. We'll take out minus 5 of a common factor into z cubed minus 1 over z cubed. And the last two terms are 10z minus 10 over z, which is the same as 10 into z minus 1 over z. But z to the n minus 1 over z to the n is 2i n sine n theta. So this gives me 2i sine 5 theta minus, well, z cubed minus 1 over z cubed is 2i sine cubed theta, but I'm timesing it by 5, so that's 10i sine 3 theta. Sorry, not sine cubed, sine 3 theta. And then z minus 1 over z is 2i sine theta times it by 10. That will give me 20i sine theta. And remember, this was my identity for 32i, sine to the 5 theta. Now, my final trigonometry should not have any i's in, and hopefully you can see at this stage, every single term on the left and the right has a factor of I, the i's will all cancel out. So essentially, if you divide through by 32i, you'll be left with sine to the 5 theta is 2i over 35i, which is 1/16 of sine 5 theta. Minus 10i over 32i, which is 5/16 sine 3 theta. Plus 20i over 32i, which I think is 5/8 sine theta, is the identity we want. Now, this method can also be used to prove mathematically useful formulae. It can't really give nice formulae, useful formulas for things like tan to the power n theta, but it can give mathematically useful formulas for expressions of the form a power of sine times a power of cos. So I want to use the method I've done today to prove that this formula for sine to the cubed times cos squared theta. And then we're going to use that to solve a certain trig equation afterwards. So if I start with the left-hand side, again, letting z equal e to the I theta, I need sine cubed theta. So I know that sine theta times by 2i is equal to z minus 1 over z. And in a minute, I'm going to cube that. So I need to cube that. And I also know that cos theta, well, I know that 2 cos theta squared is equal to z plus 1 over z. And I'm going to square that. So I'm going to start with that expression there. The thing on the left, if you expand the brackets, you just get a multiple of sine cubed, cos cubed, and I can divide through by that. The thing on the right, we'll do some sort of expansion on that in a minute. For the left-hand side, if you cube 2i, or 2 cubed is 8, I cubed is minus I. So that's going to give you 2i is going to cube to give minus 8i. This 2 is going to square to give 4. If you times them together, you will get minus 32i sine cubed theta cos squared theta is equal to. I now need to expand the thing on the right hand side. Now it's completely acceptable to expand that by doing a binomial expansion, expand that by doing a binomial expansion, and then multiply those together. There is a neat trick that makes the algebra a little bit nicer in this case, using a kind of difference of two squares logic, which is to rewrite this as z minus 1 over z times z minus 1 over z all squared times z plus 1 over z all squared. Now those two there are the squares of a minus b times a plus b. And we know that a minus b times a plus b is the same as a squared minus b squared. So consequently, a minus b squared times a plus b squared will be a squared minus b squared squared. And I can use that on those terms. It does not essentially, it makes the algebra a little bit nicer, otherwise it gets a bit messy. So I'll leave the z minus 1 over z in front. The other two terms are the same as z squared minus 1 over z squared all squared. Now you can just square out the bracket. I mean, you can do a binomial expansion, but you can just do it by thinking it's z minus 1 over z squared times another z squared minus 1 over z squared. So you're going to get z minus 1 over z into z squared squared is z to the 4. Z squared times 1 over z squared is minus 1. Times it again, you get minus 2 plus 1 over z to the 4. Do not write this back in terms of trig functions yet. Let's just expand the brackets and see what we get. So that's going to give me z to the 5 minus 2z plus 1 over z cubed. That's timesing through by z. And then timesing through by minus 1 over z is going to give me minus z cubed minus 2 over z, so plus 2 over z, minus 1 over z times minus 2 is plus 2 over z, and then finally minus 1 over z to the 5. And then I am going to collect my z to the n and 1 over z to the n terms together. That's okay. So I can do that on the next line. I'm going to slightly run out of space, but I can cheat a little bit. So that is the same as z to the 5 minus 1 over z to the 5. Cancelling that out. I've got minus z cubed plus 1 over z cubed. So that's the same as minus z cubed, take away 1 over z cubed. And then finally, I've got minus 2z plus 2 over z, which is minus 2 into z minus 1 over z. Now, my friends, we are nearly there. So z to the 5 minus 1 over z to the 5 is the same as 2i sine 5 theta. So that's going to give me 2i sine 5 theta. Z cubed minus 1 over z cubed is 2i sine 3 theta. So it's minus 2i sine 3 theta. And then finally, z minus 1 over z is 2i sine theta times it by 2 gives minus 4i sine theta. Now, if we get as far as this, ladies and gentlemen, boys and girls, I think we're okay. If you divide everything through by minus 32i, the identity we are looking for comes up. So that leaves me with this dividing through by minus 32. Let's create a little bit more space down here. I end up with sine cubed theta cos squared theta is 2i divided by minus 32i is minus 1/16 sine 5 theta. Minus 2i divided by minus 32i is plus 1/16 sine 3 theta. And then finally, minus 4i divided by minus 32i is plus 1/8 sine theta. And we are done. Now, as explained earlier, one application of this kind of identity was to help integrate, and you can indeed use this to integrate this function quite nicely. There are also certain trig equations which can be simplified and solved using these kind of identities. So this equation I need to solve is the equation sine 5 theta is equal to 3 sine theta 2 sine theta. I'm going to solve it for theta, presumably in radians, between minus pi and pi. And there's not an overall method for this. What I'm going to try to think about doing is, can I rewrite this equation somehow using my previous identity, and then hope and pray that that will lead it to an easier equation to solve. And what I'm going to focus on is this, but there is a genius way of spot, which you might spot for this, is let's get rid of the sine 5 theta. So the previous identity, if you make sine 5 theta the subject, it gives you the following. So we'll take the sine to the 5 theta term across, and the sine cubed cos squared back, and then times through by 16. So the identity shows me that sine 5 theta is, I'm going to have sine cubed cos squared on the other side, but times, it's going to be negative, but I've times it by 16. So minus 16 sine cubed theta cos squared theta plus sine 3 theta plus 2 theta. That's just rearranging that to make sine 5 theta the subject. So therefore, the equation becomes minus 16 sine cubed theta cos squared theta plus sine 3 theta plus 2 sine theta is equal to sine 3 theta plus 2 sine theta. And then you note some really nice things happen, which is that and that cancel out, and that cancel out. So that just gives me minus 16 sine cubed theta cos squared theta is equal to 0. And there are other ways to get to this stage, but this was a decent one. A slightly odd looking trig equation, but basically I can divide through by minus 16 because that can't equal 0. That gives me that sine cubed theta is 0. So sine cubed theta times cos squared theta is 0. But two things can only give 0 if either the first is 0, sine cubed theta is 0, or the second is 0, cos squared theta is 0. You can then cube root both sides, and that means that sine theta is 0, which is now an easy equation to solve. Or if you square root both sides in the second one, you get that cos theta is equal to 0. So we've turned this horrible equation into two elementary trig equations. If you solve sine theta is 0, if you inverse sine it, you will get theta is 0. The other solutions in radians, which come from the graph of sine, are at plus or minus pi. If you do inverse cos of 0, you will get theta is equal to pi over 2, which is a half pi. Again, using the symmetry of the graph, you get theta is pi minus pi over 2 as well. And we are done. Okay, so you may now attempt the exercise following this to practice what we've done today. Okay.